Oh, okay, so this red floor is actually disconnected from the rest of it.
Yes, this is the isolation joint here. And the red floor is part of the office and the lab space and is connected to the building. And then the white floor, it's a lot thicker, and that's the floating slab.
What's the difference between a synchrotron and a cyclotron?
The cyclotron doesn't store the beam, whereas the synchrotron can ramp up in energy and store the beam.
Got it.
So you will see a lot of cyclotrons in hospitals where they just need to generate an energetic beam to produce radiopharmaceuticals. So there they actually don't need to store the beam. What they need to do is smash the beam into material and make it radioactive so they can inject it into the patient to do imaging and diagnosis.
Right.
Whereas here we want to store the beam because we want to use the photons that are emitted by the beam as they circulate. So the acceleration in the circle generates synchrotron radiation, which is what we use. Whereas the other facilities, by and large, want to smash particles into a target.
And that's the Large Hadron Collider.
Large Hadron Collider that wants to smash particles into particles.
Yep.
And medical facilities, here's an example of a cyclotron.
Yep.
Where the beam spirals out.
Ah, right.
And then you have an energetic beam and you smash it into a target.
Got it.
Whereas with the storage ring and a synchrotron, you ramp up the energy to some value and then you keep it at that value because you're looking at the radiation that's emitted by the stored beam, not smashing into anything.
And what is synchrotron radiation? Can you give a dummy's guide for what synchrotron radiation is?
What it is, it's essentially like you think of the radiation emitted from a radio transmitter. It's the same principle. In a radio transmitter, you're accelerating an electric charge and you're disturbing the field lines of that charge. So if you have a static charge, you just have a charge and you have field lines coming off that. And so there's no change in those field lines. As soon as you move that charge, the field lines change. And what are oscillating field lines? Well, an electromagnetic wave, oscillating electric and magnetic. So as soon as you move a charge, you generate radiation. So synchrotron radiation specifically refers to, in most cases, a relativistic charge generating high energy radiation. So, but in terms of the physics, it's more or less the same principle as a radio transmitter. And it's but the term synchrotron radiation is used in astrophysics, with the high energy processes out there in the universe, and also with particle accelerators for high energy beams. From here we can see very interestingly the different types of radiation that's produced by the Australian Synchrotron. In front of us here we have a conventional style infrared lab. We get a very nice small spot and our infrared, so we can get very high resolution infrared scans. So that's one of the advantages you have with the synchrotron.
How do they scan? How do they scan it?
Just
do they
mechanically,
beam? Oh, they just
move the
mechanically
sample.
Move the sample.
Yeah.
That's it. But I thought it had like a resolution of nanometers or something.
But this is a long wavelength infrared,
long
so
wavelength
it doesn't make
infrared,
sense to
of
have
course it doesn't.
nanometers
Right,
because
some of
that's
the
not
other
your.
ones, some of
The other ones do. They have 100 nanometer resolution.
And how would they still those? Would they still do it actually physically, mechanically move the
mechanically
sample?
move the sample. The beam
Right.
would jerk around too much, but you can
if
get
you tried
very
to steer it,
stable mechanical stages. Yeah.
Right.
Plus, if you steer it for one, then it's not the right steering for the other, and we've got 14 stations to consider.
Ah, got it. I thought each beamline would be able to steer its own once it comes out.
Not
It'd be able to steer it
Not entirely.
Self?
Yeah.
Right.
It turns out that it's more stable at moving the sample.
Got it. Okay.
And then you can see that going up higher up in energy, there's a ultraviolet and soft X-ray beamline over there, and that doesn't require much shielding either because the X-rays are absorbed by only a few millimeters of stainless steel.
Right.
And then over there, the big aqua turquoise lead box that contains a beamline which does protein crystallography, where you shine a beam straight through your sample, and that's in the hard X-ray regime.
Got it.
So you get the long wavelengths, shorter wavelengths, and then the shortest wavelength. We can go over and have a look at the end station of the soft X-ray in a little more detail.
Can those beam lines be positioned effectively anywhere along the around the storage ring, or do they have to be in specific locations for specific reasons?
They're more or less anywhere, but they are driven by special magnet arrays. So there's a set of magnets which store the beam and confine the beam, and then in between those magnets you can generate interesting paths for the beam to go on. Well, as long as you preserve the symmetry coming in and the symmetry going out, you can actually wiggle the beam back and forth in interesting ways and generate a particular wavelength that you're interested in, or you can tune the wavelength coming down your beam line so it doesn't disturb the wavelength coming down the other beam lines.
That's why in the optical one, Tom's optical one before, we saw that yes, they were able to change the wavelength into optical for use.
Exactly.
To determine the quality of the... Now this is some impressive shiny metal. We love this stuff. Tell us about this.
This is essentially taking advantage of Einstein's photoelectric effect. So you put a sample in vacuum in one of these chambers, you shine the soft X-rays on to the surface of the material. That material will then emit electrons via the photoelectric effect. So electrons are bound in an atom. You add energy through an X-ray that then liberates the electron from the material, and then it goes through this electron energy spectrum analyzer. So this hemispherical detector there will measure the energy of the electron that comes off the sample. So you have a known energy of photon coming in onto your sample, a known energy of the electron coming out, and from that then you can then deduce what's going on in your sample. So you measure the known properties, and then you can determine some unknown properties of material.
Because effectively what this whole facility, synchrotron facility, is just a light generator basically, isn't it? Is that a correct term to use?
Light in a very
light over
general
a full,
sense.
What wavelengths can you go from? Infrared up to?
So to use the physics term, you're taking a slice of the electromagnetic spectrum.
Yes. So
you're going from the long wavelength end of the spectrum at infrared all the way up to the hard X-ray end of the spectrum. So you're going from less than EV up to hundreds of keV in energy, and everywhere in between. And you can tune the magnets that are dedicated to the insertion device beam lines and adjust the energy of photons that are coming out. So photon is a physics term for a packet of energy. It's light, it's electromagnetic. So we use kind of interchangeably light, photons, X-rays, infrared. It's more or less the same stuff. You just have to modify how you analyze it and what type of information you're going to get out of your experiment and how you probe matter. So if you want to just look at the surface of things, you use the low energy photons, and if you want to do some more penetrative work or do some imaging or do some other X-ray fluorescence analysis, then you need to have the higher energy X-rays.
Because you can do 3D X-ray imaging with this thing, can't you?
You can, and in fact we've done that on our medical imaging beam line.
Yep. But once again, that's done by moving the physical object around to scan it, and then that gives you a 2D result, and then they process it into 3D, is that correct?
Yes, so you just do the mathematics of the CT analysis and computer tomography. So if you get information along a line in your sample and you move that sample around, then you can combine all the other bits of information to deduce what's happening in 3 dimensions.
Got it. And all of that's done with the one storage ring. You can do all these different experiments off the one ring without having to change what's in the ring.
Yeah, because the ring has its constraints to store the beam stably, but then you have some degrees of freedom on each of the individual beam lines and on the end stations looking at the photon beam. And in fact, on one beam line, they've done 4-dimensional imaging where the fourth dimension is the elemental composition. So not only do you get a density profile, in fact you could probably call it 5 dimensions. So you get density, and you also get elemental composition.
And you get all that over time as well, wouldn't you?
Unfortunately, you need a static sample because it takes too long to take all the images from all the angles to have the sample also being dynamic, because as soon as that sample is dynamic and it's not stable on a timescale of days...
Oh, you'd need days to take a measurement sometimes.
You'd need many hours, so the sample needs to be static on a timescale of more than days, otherwise the time over which you're imaging it, it's not valid, then the mathematics won't be valid, because you've took this angle at one time, this angle another time. If you don't make the assumption that you're looking at the same thing, then the maths doesn't work. Because if something's moved, then you saw it from one angle and then you saw it from another angle, and you don't know which way it will have moved. So it needs to be studied. So there are time limitations as well.
And for those really fine surface measurements where you're moving the sample, how do you ensure it doesn't move over the course of a couple of hours? Like, if you get minor little earthquakes somewhere, can that sort of, or if you've really got good anti-vibration tables, and
a lot of really good
be...
anti-vibration tables, and
okay.
you can see even here with these pumps on the ground here, they can isolate those vibration. You can see there's various isolation joints and springs and
got it, because they would certainly couple a lot of even the fans in the some fans in racks and things like that, you'd have to be very careful about.
So you just have to be careful about how you engineer it. So it's just very well engineered and precision controlled, so that you can, within the time scale of your measurement, you can ensure that that's not a limiting factor, that the vibration is not a limiting factor in being able to make the measurement.
And who sets up these beamline projects? Do universities bid, or do companies bid? Are any of them private, or are they? It's
a collaboration. So there's in-house knowledge as to how the beamline can perform, what the parameters are, what type of samples can be used, and just experience with doing scientific experiments. Then there are universities predominantly that come up with the ideas for the experiments, and what often happens is that the universities and the researchers there have the research groups that are working on the implications or the applications or the use of the data that's generated here. So sometimes the scientists who are doing the measurement here, they will know how to take the data and generate the information that they need, and then the researchers will then apply that to their particular area of research and turn that information and that data into new knowledge. So often the users here, they use the scientists here to get their data, but then they take that data away to their lab and analyze it and apply it to their particular project that they're working on.
And the same data could have broad application, potentially, sometimes.
It could, but because there are so many settings and so many parameters and so many variables, that it's very hard for the researchers themselves even to keep track of that, let alone for that to be communicated for someone else to use that data. There are some exceptions, like you also asked about industry. There are some industry, and the most obvious ones are the mining industry and the pharmaceutical industry. They could come in with a very standard type of measurement. What's the element in this sample? Where are the proteins in this particular sample? And then they can go off and say, right, we've got gold in them there hills, or we have this particular type of protein which we know does X, Y, Z in a biological system. And if they want just to have that information, walk in, have the service done, walk away and keep all that information for themselves, they have to pay for that. There's only a small percentage of people that do that. Most of them are pie-in-the-sky research projects where they come in with a grand idea, it gets reviewed, gets given some beam time, and then they walk off, and they may or may not come up with a great discovery. And it's just part of fundamental research that we try and discover what's going on in nature, and we use these fine bits of equipment here to study in as good a detail as we can what's happening out there in nature.
How does this facility compare with other synchrotrons around the world?
It's very hard to do a direct comparison because each lab will have their particular world-beating technique or world-beating, because it covers such a breadth of photon range, such a breadth of science discipline, such a breadth of equipment that it's very hard to come up with an all-encompassing response to that. I can highlight a couple of things. For example, on the Accelerator, we've set a world record low vertical beam emittance, more or less the beam size, and that's down to about a picometer beam size. So when we specially adjust our skew quadrupoles and really tune our beam stability, we can get a world record low beam, which is about a picometer.
A picometer, that's the thickness of the
beam.
The thickness or the diameter? It's a
1 sigma thickness of the beam.
Right,
so,
got it. And that's all to do with the magnetics, essentially.
Yes, tuning the accelerator. On another example on the beam line, there they have a very clever detector which can detect in less than a few milliseconds on maybe a few 100 nanometer spot size. It can detect the elemental composition on that particular point on a sample.
Wow. And
so
then you could scan the sample.
And so you scan the sample, and so you can get in kind of 100 nanometer steps.
Wow.
You can figure out what percentage of what element is on each point, and so you can come up with these elemental composition maps on an incredibly fine scale. One of the things that they're using that for is to look at where the micronutrients is in grains. So you take a piece of rice, say, slice it up, put it in the beam, and scan the sample along the beam and find out where the essential nutrients are in that grain, and then you, in your agricultural research, you will then try and optimize and get the most nutrients into the grain that people are going to ingest.
Because you might find that 90% of it is nothing, it's just useless.
Well, the problem is that most of it's in the husk.
Oh, right.
And it's kind of culturally the case where you take the husk away and you eat the white rice.
All right, I'm here with Tom, and he's working on one of the beam lines, the visible light beam line. Is that correct?
Yes.
Tell us what you do here.
So this is the optics beam line at the Australian Synchrotron. So we use this beam line for diagnostic purposes. This is
what sort of diagnostics?
So we use diagnostics to find different properties of the electron beam,
right,
which is located behind this wall. We have from the synchrotron itself. One of the properties of electron beams and even proton beams, when they get to high enough energies, is that they will actually output radiation when they are put inside a magnetic field. Yep. So this radiation
and go around a bend.
When they go,
they have to be going around a bend, don't they?
Well, with the application of a magnetic field, they'll generally be accelerating in one form or another. So, as it can be seen, that the radiation is output in, as we said earlier, in the visible spectrum here. Mm-hmm. We use the visible spectrum because it's easier for diagnostic purposes. It's quite hard to use the IR, UV and X-ray regions for diagnostic purposes, and it can be a bit dangerous if you go into those higher energy.
Sure.
So this beam can then be used to actually diagnose different properties of the electron beam itself in the synchrotron. So this beam can be output onto our optics bench, which we have here.
Yep. And these optics benches have to be very precisely leveled, don't they? And vibration free as well?
Vibration free. We are actually, the floor we are standing on of the whole facility is actually damped. So that's different.
How do they do that? Is it spring based or?
It is, I think it's floating on a form of player.
Oh.
From what I recall.
Interesting.
But I'm not 100% sure about that one, but from what I recall of hearing. But this beam can be output onto any of these, and using these different like optical mechanics and lenses, we can find things like the fill pattern of the machine itself. The fill pattern is the amount of electrons in a given bunch throughout the machine. We can also find we can diagnose instabilities in the bunch. So if we find that there's an instability, we can either correct these before we lose the beam. And it is important not to have any of these instabilities because the beam lines want to have as constant synchrotron radiation output, generally in the X-ray, UV, and IR region for the actual biological purposes. And
how do they change the wavelength of what's coming out of the synchrotron? Is it one wavelength in the synchrotron, then you can change it when it comes out of the beam line, or how does that work?
Each of the beam lines uses a device called an insertion device to produce the actual radiation. The insertion device itself is effectively, there are actually multiple types. There's a wiggler, there's an undulator, and then there's bending magnets.
Got it.
We use bending magnets here in the optics beam line. We've actually just installed the superconducting wiggler.
Excellent.
Actually, in the last week or so.
Great T-shirt slogan: superconducting wiggler.
So that's just been installed. So a wiggler is actually just an insertion device. So instead of a bending magnet, which has a single magnet, which will bend the beam, this will undulate the beam backwards and forth. Right. And this will produce kind of waves of electromagnetic radiation
at the specific frequency you require.
At a specific frequency.
Got it.
With the higher the actual magnetic field, the higher the energy, because it's going to bend on a shorter bending radius.
And this one's designed to produce visible light at what? It's pulsed, isn't it?
It is pulsed. The beam is pulsed at approximately 1 gigahertz, and each bunch length is 23 picoseconds. 23 picoseconds. So it takes quite advanced equipment to pick up.
Can imagine.
Different properties of those 23 picosecond bunches. We can see here that we've got a picosecond digitalizer.
Yep. So you can, with this beam line and this gear, you can determine the quality of the beam itself in the synchrotron. That's what this room's for. Yes. Basically. Got it.
Exactly.
Okay. And is that an ongoing measurement, or do you just do it periodically, or before a critical measurement? Or
we do a lot of things ongoing.
Yep.
We have a control room which is located on the other side of the facility, and they will use generally electrode pickups that are actually placed in the beam itself.
Oh, okay.
But we can use also the optics bench, and mainly we use the optics bench for developing new types of systems to actually take these measurements. And then we can go have a look at some data that I've taken out of.
Excellent. Let's do it.
The synchrotron itself.
All right. Give us a look at some data.
Okay, so what we've got here is the outside of the optics beamline. So we can we use all these here to process all the data, and as you can see over here, we've got a few different outputs from the beam itself. Yep. So these are from pickups that are placed inside the beam.
Got it.
So each of the beams will have different things like a beam position monitor and other devices that can detect different like electric and magnetic fields produced by the electron beam.
Right.
So as you can see here, we've got this one, which is the amount of, this is a loss detector apparently, according to its
label.
According to its label, which is being picked up on this scope here, this oscilloscope. So this is these are the general oscilloscopes we're using at 600 megahertz oscilloscope.
Toy stuff.
Exactly. Yeah. So we have a slightly larger oscilloscope over there.
And these are all signal amplifiers, are they?
So each of these, a lot of this is actually timing. Right. So a lot of these will be, you can use as triggers for each of your, the samples that you're taking out.
Got it.
So you can get from here the trigger for the actual revolution frequency, and then you can get different triggers to help you clean up your sample of it.
Right. Beautiful.
So then, okay. So what we've got here is one of the computers we use for diagnostic purposes. So as you can see here, there are a few different GUIs to keep an eye on different parameters of the beam.
Yep.
As you can see here, we've got the beam current, the current per injection, because we're currently at a mode where we're constantly injecting rather than allowing the beam to reduce in energy and then doing a much larger injection, because it produces a much nicer beam for the different beam lines.
But the beam current is still 200 milliamps.
200 milliamps.
So is that are the injection ones modulated on top of that, or how does that?
So it effectively you lose the actual beam due to different, like, I'm trying to think of the word. It's like attenuation, but it's it's the non-physics word for attenuation.
Oh, okay. And what have we got here? This is
what we got here is the beam current being displayed over a timescale of hours. So
why does it have a little sawtooth pattern in it?
So the sawtooth is due to the loss of the slow reduction of the current, and which will be lost due to the fact that the vacuum isn't actually a perfect vacuum. There are particles in the beam.
Okay, so there's but if it was perfect, then it would be, well, it'd be continuous, wouldn't it? It'd be lossless.
It would be lossless.
Yeah.
Though there's always going to be different things which can remove it, including instabilities as well. They can also result in loss of beam current. So does the one beam's used for all the different beam line projects, isn't it? So yes.
So they all tap off the one. They all tap off the one beam.
Yeah, we have one. We can actually go to this diagram here, which displays the synchrotron we have here. So we can move that one across. Yeah. So what we have is the beam starts right here at the electron gun. The electron gun puts out a 90 keV.
90 keV,
electron.
It's about 3 times a regular TV CRT or something like that.
About that, yep. And then we go into the LINAC, which is the linear accelerator. This will accelerate using a bunch of RF cavities up to 100 MeV.
Yep.
We then pass through to the LINAC to booster ring. The booster ring is the actual synchrotron itself.
Right.
The outer ring is actually not a synchrotron.
Oh, it's a storage ring, isn't it?
It's a storage ring, yeah.
Got it.
So the electrons then pass into this booster ring, and they are given energy up to 3 GeV. And once they achieve this 3 GeV energy, they can be injected into the storage ring itself, and then the electron beam will continue to pass around this storage ring, being given a given amount of energy each revolution to account for energy loss.
Due to the vacuum only. Is that the only loss, or do you get loss around bends and?
You get loss around bends, and that loss in energy is actually the synchrotron radiation itself.
Oh, of course. Yeah, yes. Energy's got to come out, right? You're extracting energy from it. Right? But in theory, if you had a perfect storage ring, you could put you could store it in there indefinitely if you didn't extract any energy from it.
If Synchrotron
theory.
radiation didn't
It
exist.
didn't exist and didn't happen, but it happens
So,
on
but it
any
happens.
time you bend.
Anytime a charged particle is bent.
Is bent,
Yeah.
right. And bent is another word for accelerated
Yes,
in
it is.
physics, isn't it?
Yes.
Accelerate's not actually accelerating in speed,
It's changing in. It's effectively
changing
changing
the
in
direction.
direction. Yeah.
Yep.
It's an acceleration in any axis. So what we've got here is each of the beam lines that can be installed. So we currently have 9 beam lines, with the newest one being input lately.
Right.
Which, if we just back up a bit, we can actually see the new medical beam line.
Oh, okay.
So
That's
next-
a radiotherapy.
So
one, is
next
it? Oh,
to
no. Yeah.
see this, the imaging and medical beam line. This
Yep.
is where we've just installed our latest insertion device, which is a superconducting wiggler,
Superconducting wiggler. Woohoo!
which is cooled using liquid helium
Excellent.
at negative 270 degrees Celsius.
Fantastic.
So, very cool, as a lot of people have.
And I take it that light on the outside is to tell you that
That's
it's
to
in
tell you.
operation.
So each of the lights, it just tells you what stage it's in. So if it's green, people can go in,
Yep.
and the orange is more of a caution that
Mm-hmm.
you should, don't go in, don't go in unless you have to.
Yep.
And red means the beam's on.
Got it.
So as you can see, the red light over here.
Oh, okay. So you can't go in those rooms when the beam's on.
Can't go in those
Right.
rooms.
But we
You'll
can
be-
go in the one, but the optic one we were just in here.
But we can go
Not
in
a
the
problem.
optic one
Yep.
because it is at the end of the beamline itself. It is actually not next to the
Got it.
the storage ring itself.
Right.
So between there and the storage ring, there is thick sheets of cement to protect us from the radiation.
Right. Cement is better than lead.
Cement,
something?
Cement is cheaper and lighter than lead.
Cheaper and lighter than lead. Got it. Why do you use electrons in there? You said you could use positrons.
You can use protons.
Protons.
You can use protons, but electrons, due to their much lower mass, actually produce synchrotron radiation at much lower energies. So if the amount of radiation produced is inversely proportional to their mass by a factor of m to the 4, or e to the 4, because e and m are proportional. So we therefore, using an electron which has a rest mass energy of 511 keV is better than using the 1 GeV proton.
Got it. And this facility is a 3
3
gig
GeV.
electron volt
Giga-electron
facility. How does that fare in the world scheme of synchrotrons? Is it a
So 3 GeV for a light source is quite a common energy.
right?
So most third generation light sources are around 3 GeV. You can get some much higher energies up to like 9 GeV. Though for the LHC, which is over there,
That's
which is
teravolts,
accelerating,
isn't it?
which is accelerating the protons, they are working up to 14 tera-electron volts.
14 tera electrons. Incredible. And that's a great t-shirt, by the way. Physics is the bomb. Oh, I love it. And we have some big engineering here. Tell us about it.
We do. These are the magnets that are actually used inside the storage ring. So each of these has a specific purpose for the beam. We've got the dipoles, which are used for the actual bending of the magnet, of the beam.
Right.
So the dipoles are also known as the bending magnets. So they allow the beam to actually continue in the approximately circular path.
Yeah, it's not actually.
It's
That's
not actually
it's circular. It's a misnomer. It's straight bend, straight bend. Right.
It's a very, very excessively 50-cent piece-like structure.
Right. Yes.
So these are the quadrupole magnets. The quadrupole magnets are used for focusing and defocusing, the same way in which an optical lens focuses. Though with a magnet, with a quadrupole magnet, when a beam passes through there, you can't actually focus in each axis at the same time. You must focus in one and defocus in the other.
Right.
due to the way the electric fields are, but we can still use the common optics principles that if you focus, defocus, and focus again, you can actually decrease the beam itself. So then we also have the Quadrupole Magnet, which is used for higher order effects on the beam, and these are used for changing things like the chromaticity beam, which is actually the spread of the energy.
Right, that's what chromaticity is.
That's what chromaticity is.
Right. And these are there. So there's not many turns in these, but they're like almost bus bar like. Yeah. How much current goes through these? Do you have any idea? Mark's going to tell us.
I think they're about
up to and over 100, depends on which set of coils.
Right, up to over 100 amps.
Because you might see that they're actually different sets of windings.
Yep.
So there's the primary set of windings under here, and then there are these different set of windings with different number of turns.
Ah, right.
So these magnets can also be used to generate a dipole field in this direction, a dipole field in this direction, and a skew quadrupole field, which is a quadrupole like the red ones over there, but rotated.
Got it.
So you can do coupling correction when the beam is meant to be oscillating purely up and down and purely left and right. Sometimes you get coupling where it spirals round, oscillates in one plane and then goes into the other plane. You can then correct that.
Got it. You can fix that in real time. Fix that dynamically in real time.
It's a static setting.
Oh, it's a static setting. Right. Okay.
You set it, and basically what you're doing is if the magnet isn't installed properly, it might be slightly off axis. So instead of focusing the beam in the true vertical plane, it would focus it slightly in that plane, and so you would then wire up these coils to slightly correct that.
Here we've got the linac, which is where the beam starts.
Yep.
So, as was said before, there we've got the electron gun inside here, which will output at the 90 keV beam.
That's that's thermal. It's just heats up a cathode and right. So it's thermionic emission. That's pretty boring, I guess. It's just a little cathode and.
It's an old TV.
Yeah, right. Okay.
So the cathode then will outputs that, and that is injected into the linear accelerator. Yep. Which we've got here. So we've got here. You can see the bunch of keys. So nobody can go into the linac and get stuck in there while we turn the machine on.
Right. So it's actually dangerous technically inside the inside the linac.
Throughout the machine there is radiation being produced.
Right.
So, and this is what all the large thick walls that we have surrounding the facility are for, to absorb all this radiation.
Right, okay, so these are all the thick concrete walls.
So
yep.
As you can see around here, this allows us to reduce the amount of the dose that the people that work at the facility get.
Okay. Is there a maximum amount of time that they're allowed to spend in the facility, like around here, or? There we go. Hey, we can see inside. Woo! I'm being irradiated right now. Terrific. Oh, I better cover my private parts as I walk past. Could be in trouble.
So there.
Right, so we can actually see why it's blue in there. I can see like. I can't get it on camera, but
it's just a blue light. It's not.
Come on! Just a blue light, folks. That's boring.
So there is a limit to the amount of dose you're allowed to get per year.
Per year, right? Year. Okay.
you might just say,
what's all?
These are Kystron RF amplifiers.
I don't know much about them.
You just repeat what I say. So these are Kystron RF amplifiers, and they have a peak power of 35 megawatts each.
Ooh, I can say that.
So what we've got here is the Kystron amplifiers, and these have a peak power of 35 megawatts.
35 megawatts. That's ridiculous. That's incredible.
So these are the actual power source for the RF systems in the linear accelerator, and allowing the beam to be accelerated from 90 kV up to 100 million electron volts, or 100 mega electron volts.
Right, and it does that in what, 10 or 15 meters or something? Like that, I think?
Approximately 10 meters.
Right, got it. And obviously these are very efficient, I would presume. Statement, because if you're producing that much energy, any percentage waste has got to come out as heat. So
that's what happens.
right, and then they're not that hot, folks. There's a bit of warmth coming out of there, but
the heat's dissipated in the copper accelerating structures in the linac.
Got it.
These only come on for a 10 microsecond
burst.
window. That's
okay.
why it's a peak power that's so high, but the duty cycle is very low.
Right, so the average power is actually relatively low. Got it. And these are all power supplies, are they? Power supply systems or control racks?
Yeah, so there are 14 sectors.
Yep.
Each sector has power supply rack for the multipole magnets.
Right.
The electronics for the beam position monitoring, and the vacuum monitoring and control system.
Got it. And so there'll be 14 of these stations all up.
14 for in the storage ring, and
right.
then another set for the linac and booster ring.
Got it. Because this outside ring, this is the storage ring on the outside, correct? And then on the inside here is our booster, linac and the booster ring.
Let's go up on top of the booster and the linac.
All right. All right. Up we go.
Yeah, the linac is pointing towards us underneath the
I see, right.
concrete in the vault.
Yep.
And then it goes down underneath our feet and around and into the booster.
Right, so this, so that's the inner circular booster ring. And then where does it shoot out into the storage ring?
On the far side where that blue
right.
light is.
Oh, got it. Okay.
And then it connects to the storage ring over there.
Got it.
So we could build a linear accelerator which is 30 times as long as the one we have here.
Right.
And get to 3 GeV. But what we've done is we've done a more efficient technique where we put it through this booster ring where every lap it does, it gains a little bit of energy, and so you keep passing it through the same RF field. So it would do probably a million laps.
A million laps in a couple of seconds?
In half a second.
Right, yep.
And then get extracted into the storage ring where it can stay for days at a time.
All right, what have we got here?
Okay, so what we got here is the outputs of some of the beam position monitors that we have inside the storage ring itself. So we can see each of these will have an output signal which is indicated above here. So these can be used primarily to know the beam's position, to make sure the beam isn't going to actually run into any of the walls of the beam pipe itself. So, which is always
what diameter is the beam pipe? It's stainless steel, isn't it?
It's stainless steel.
Yep.
And it is approximately a couple of centimeters.
Right. And does it need really thick walls on it, or is it just like a regular size aluminium tube?
It's a pretty regular thickness, like a couple of mil thickness. So there's no need for extremely thick walls. And
they're all straight sections, correct?
So the sections in here are all straight.
They're all straight. Yep.
Yeah, and the actual curvature itself comes from the parts inside the dipoles.
Right. And so you could actually build this facility as a straight line if you really wanted to,
yes,
correct?
There are facilities around the world where there are completely straight facilities, like the one in Stanford.
Oh, okay.
Is a good example where you effectively use the principle in the linear accelerator and continue that on for many, many kilometres.
Right, okay. But this is, I guess, more space efficient.
Much more space efficient, yes.
Got it. But would it cost more, a facility like this, because you have to have the curvature in it? I wonder.
I would say that the circular facilities actually cost a fair bit less due to the much smaller region they actually have to cover. The linear accelerators in like Stanford is 4 or so kilometres long from what I recall, so it's quite a large facility.
Right.
So you could imagine the cost of making the tunnels and everything like that.
So they actually bury that one underground. They actually tunneled that out.
A lot of that is underground.
Right.
Yeah.
Okay. Why is that? Is there any reason why it has to be underground, or is it a cosmic radiation thing, or is it a?
It's I think it's to put it on the clay for stability, but I'm not 100% sure on that one.
That makes sense. And
so what we got here is actually a bit of a rubbish signal because I don't have anything input yet.
And check it out, folks. Yes, at this multi-$100 million facility, we have a breadboard.
This is
brilliant.
This is a quick prototype I've been making lately, just to.
And let me guess, it uses a 741 op amp and a 555 timer.
No.
No? Oh, damn it! Come on, we need to have a 555 timer here.
So what we can actually see here is the signal from one of the beam position monitors itself. Each one of these is an indication of the amount of electrons in each of the bunches. So, and for each of these is 1 revolution.
Oh, okay. It's done a full cycle of the storage ring.
Of the storage ring, yeah.
Right.
So the frequency at which each of these large bunches will occur is 1.388 megahertz.
Right.
So if we can actually zoom in and see to an extent due to the bandwidth of the scope.
Right.
The each of the different bunches inside it, you can't see them as well. Just
okay, so they're the individual bunches. Of course, they're the individual bunches of 1 nanosecond.
Of 23 picosecond.
23 picosecond.
Of course,
the
600 megahertz scope will never be able to pick them up.
Would the sensors be able to pick them up?
A lot of the sensors can't pick them up.
Right. No, I was going to say they wouldn't.
We're currently, we have built. One of my fellow colleagues has actually built a system which works on synchrotron radiation to pick up these 23 picosecond bunches.
Wow, that's impressive physics in its own right, isn't it?
Yes.
Because
it's quite an impressive bandwidth to be working at.
So it's art and science just to design the detectors, just to see the position of these things flying around, let alone the equipment in the beam lines that's designed to analyse the stuff. It's incredible.
A lot of this we end up doing blind to a lot of the things on the very small scale.
Right, okay.
Part of it's just a low pass filter I'm putting in my system. And then we'll be...
Right, so it's just an op amp low pass filter and that's it.
Yep. Oh, and then it'll be, what it's going to actually do is find the different changes in the amplitudes in each of the single bunches.
Yep.
And this will be able to take what's called a tune, which is a tune is the actual oscillation, which is the beam oscillates at. So this will be able to detect the tune without the necessity, which at the moment we actually have to to undulate, like to do a small perturbation of the beam. So this will allow us to actually pick up completely passively.
Right.
Which is, it's important for the actual synchrotron radiation output, because if you're continually perturbating the beam, you get the people with the beam lines not too happy about the flickering lights.
I was just about to ask, because you've got so many potential, up to 14 potential scientists all working on their own little project at the end of their individual beam lines, or 9, I think you said. I mean, how can you just go in and change the main storage thing? You know, you're going to upset their experiments if you do that. So I assume it has to be well planned, agreed by all parties involved, and
we've got quite a well planned structure. We'll have different times for the users. At the moment, we're currently in user beam. We have times for machine studies, which is generally the physics and the operations group, for us to use the machine and to do diagnostic purposes
and play around with breadboards
breadboards
and stuff like that.
To fix any problems with the machines is around the same time as maintenance and machine studies generally overlap a bit.
Yep.
So and to also have personalised beams, so that we aren't always using the 200 milliamp beam. So a lot of the stuff I'm working on uses we use single bunch beams, which gets, rather than having 200 milliamps spread out over approximately a microsecond or so, we're talking about 10 milliamps spread out over a nanosecond.
Right.
So it's quite.
So that is the storage capacity of the ring, 200 milliamps.
200 milliamps.
So that's the maximum storage capacity.
We can go slightly higher, but that's the maximum at which it's safe and that we know that nothing will go wrong.
Why is it specified in milliamps like that? Because that's the first time I've heard that term used. Is it only used for these storage rings, or is that terminology also used for the accelerators where they smash the atoms together?
So I think we mainly use milliamps just due to the fact that it's an electron bunch.
It's a flow of electrons, isn't it? It's a continuous flow of electrons.
It is effectively,
except it's in a vacuum instead of...
Exactly.
Yep.
Rather than in the medium of... But yes, like places like the LHC do use intensities and stuff like that rather than milliamp current. Because I notice you've got a real-time display on your website that displays the current set in, and it's all in milliamps. It's like, because 200 milliamps sounds like nothing to us engineers, right? It's quite small in comparison to what comes out of the wall, but this is also in a vacuum, and it's quite a different...
Yep, it's a different ball game. Got it. It's also 3 giga-electron volts, yes. So
which is 3 billion volts for...
pulsed, of course.
Yes.
So, it's not continuous. Otherwise, we'd be powering the whole city of Melbourne, would we not? If it was continuous? Maybe.
It'd be far away.
I don't know. How much energy does this whole facility use? Do we know?
About 4 megawatts.
4 megawatts?
About 4 megawatts, yeah.
Do you have to have an on-site power?
We do. Out the back there is there's a power generator and a backup for if we lose power. So
Right. And that is blue for no other reason than that it looks cool, right?
I believe so. Yes. I haven't actually been told why it's blue. Just to scare people when they're into the
exactly. They think, oh, it's radiation, you know.
These are the booster ramping magnets.
All right.
Based on a principle that was actually invented by an Australian physicist, Mark Oliphant, and he invented the synchrotron acceleration principle, whereby you synchronously ramp the magnetic field as you increase the energy of the particle, so it stays on a fixed radius. And that way you don't need a big long accelerator. You can top the energy up on each revolution, because as you increase the energy of the particle, you also increase the magnetic field so that it stays on a fixed radius.
So these are all diagnostic and power supply racks?
These are also used, they've got some of the supplies for the cooling, as you can see from the orange pipes.
All right.
So a lot of the acquisition system is all through here.
It's a bit noisy in here, folks. We have a lot of rack equipment.
So we can also, this is where some of the outputs from the BPMs inside the beam. Right. So we've got these the stripline BPMs, and then we've got the button BPMs, which were not on this one.
That's a lot of gear.
The current transformer that's measuring the amount of current that's in the storage ring.
Oh, okay, so that box there is the storage ring.
Yeah, one's the storage ring,
right,
and one's the booster. So you can see there's the storage ring, direct current to current transformer measurement, and the booster one, and a spare.
Right, okay. How often does the facility stay up and running? Is there like failures very often, or?
We're up and running essentially 99% of the time that we schedule. So we've got one of the best records in the world for maintaining the beam availability.
That's impressive.
The other thing we've just done in the middle of last year is to introduce a continuous top-up, where instead of allowing the beam to slowly decay in the storage ring, every couple of minutes we just trickle feed a little bit of current into the storage ring, and so the current stays essentially constant at 200 milliamps.
We noticed that on the waveform before. There was like a Sawtooth Waveform, and that's what it is.
If you zoom right in, you can see the Sawtooth. If you zoom out over a day, it looks flat. And if you don't do continuous top-up, in about 8 hours it decays by about 40%.
Right. Okay. At what level is it still actually usable for something?
It's usable even at very low currents, but the problem is that you get these thermal drifts, and so you have to either keep adjusting your equipment, because with a very high heat load at 200 milliamps with all the x-rays on your, say, your mirror or your sample, then you have to adjust it as the heat load decreases or increases. Whereas if you keep it constant, then it'll reach thermal equilibrium and it'll be much more stable. Right here we're standing on top of the transfer line where the two rings meet.
Right.
And the booster ring extracts the beam at 3 GeV and injects it into the storage ring, where it stays stored for up to a week if everything goes well.
Right.
And then we have to stop for maintenance and give things a bit of a, look under the bonnet and kick the tyres.
Right. And Tom said this whole facility is floating or is damped in some way.
So if you look at the pylons here, they are connected deep down into the earth on one end and up into the building on the other end, but they are decoupled from the concrete floor where the accelerator sits.
Got it.
So if the building vibrates, then that vibration is damped by what is serendipitously a clay
surface,
clay soil underneath, and that also damps out any road noise. And the concrete slab that is over the top of that the building is over the top of, that is not connected to anything. It's just floating on that clay bedding. And so as that dries and as that moves and slips around as much as it can, given the constraints of the pylons, then we just readjust to that movement, but it's not directly coupled to any of the other structures to isolate the floor vibration.